The question here is, could you do an example on determining the combined stresses? In this particular example, I'm going to show you how to combine stresses due to an axial force N and a bending moment M. This is the problem that I have chosen here. We have a one-dimensional rectangular beam subjected to an axial force N, but the only problem is that the axial force is not exactly acting at the centroid of the cross-section. It has an eccentricity in the y direction, not in the z direction, but in the y direction. What this means is this is going to produce a bending moment about the z-axis, not about the y-axis, but about the z-axis. I'm interested in calculating the combined stresses at point A on a cross-section that is taken at point B. The first step of solving this problem is to go ahead and find the internal forces on the cross-section that we are interested in. So what we're going to do is to section the beam at point B and separate it into two parts, the left part and the right part, right? We will then mark the internal forces in the vertical plane in accordance with a particular sign convention. So here we will take these as the positive directions for these quantities. Shear force is acting vertically down on the left side. Bending moment is acting counterclockwise on the left side. And the axial force is a tensile force. We'll call that as P. And of course on the right side, the same quantities are going to be acting in the opposite direction. We can either use the left side or the right side to solve this problem, but here I'm going to use the right side. First we sum up the forces in the x direction, which is this direction right here. We have P acting in the negative x direction, 10 kilonewton acting in the positive x direction. So P goes in as a negative term here, and 10 goes in as a positive term, and sum of the two must be equal to 0, so that gives us a value for P. So P is calculated to be 10 kilonewton. Now we sum of the forces in the y direction, which is this direction right there. V is the only force acting in that direction, and therefore V must be equal to 0. Now here z-axis is the axis that passes through the centroid of the rectangular section. So I'm going to now take a moment about the z-axis. Sum of the moments about the z-axis must be equal to 0. So this is what we have. We have a clockwise moment, m, and so that goes in as a negative term here because I have taken the counterclockwise direction as the positive direction for the equation. And then this 10 kilonewton is going to produce a moment. So what do? You take the line of action, find the perpendicular distance to the line of action, right? So that's 20 millimeters. So 10 multiplied by 20 millimeter converted to meter here is the moment due to that force. So minus m plus 10 times 0.02 must be equal to 0. So m is calculated to be 0.2 kilonewton meter out of that. Now that we have the internal forces, we can go ahead and calculate the stresses due to each of the internal forces. The axial force P produces a uniform stress throughout the cross-section, right? So that includes point A. The magnitude of the stress is P over A. P is 10 kilonewton. A, which is the cross-sectional area of this rectangle, expressing that in meters, will be 0.12 multiplied by 0.05. And that gives us a value of 1666.67 kilopascal for sigma xx due to P. Now, due to the direction of the bending moment about the z-axis, the stress at this point is a compressive stress. So we'll put a minus sign in front of that. The magnitude of the stress due to the bending moment is my over I. M here is 0.2 kilonewton meter. Y would be the y coordinate of point A, measured from the neutral axis. That will be 25 millimeter or 0.025 meters. The second moment of inertia about the z-axis for a rectangular cross-section is 1/12 BD cubed. And B here is the dimension parallel to the axis, so that will be 0.05. And D, the depth, will be the dimension perpendicular, that will be 0.12 meter cubed, right? So that gives us a value of minus 694.44 kilopascal. Both of these are normal stresses acting on the x-plane in the x direction, and therefore combining them simply means adding them algebraically. So we get a value of 972.22 kilopascal. And it's a positive quantity, and therefore it is a tensile stress. So here's a differential element drawn around point A with that stress shown. So the combination of the axial force and the bending moment simply produces a tensile normal stress on the x-plane. Just for completeness, here I am sketching the variation of the stresses due to these individual forces and the combined stress in the y direction. The distribution due to the axial force is uniform and the magnitude is 1666.7 kilopascal. The variation of the bending stress is linear across the cross-section with a value of 0 at the centroid and a maximum compressive stress at the top of the beam. And the magnitude of that is 1666.7, and here are the calculations for that. And at the bottom of the beam you have a tensile stress whose magnitude is exactly equal to this. Now to find the combined stresses across the beam, you add this to this, right? So you can see here we have a positive 1666.7 and a negative 1666.7. So they cancel out to give you 0 stress at the top of the beam. But at the bottom of the beam, they double up. So we have a value of 3333.3 kilopascal, which is a tensile stress.